Hello everybody, my name is Alberto Taliercio and I am Professor of Structural Mechanics at the Politecnico di Milano, that is the Technical University of Milan in Italy. This is the first of a series of lessons on the allowable stress criteria for three-dimensional bodies. What is our goal? Well, assume that we have been able to compute the stress in a three-dimensional body. It is now necessary to assess whether or not the computed stress at any point is actually compatible with the strength properties of the material that makes up the body at that point. Otherwise, the material might crack or yield or experience other forms of damage. If the stress was computed according to a linear elastic analysis, we must check that the material does behave elastically under the working stress. Otherwise, the computed stress will be simply meaningless, as it does not satisfy the assumptions under which it was computed. Well, generally speaking, we have to verify that the computed stress is permissible, meaning that it is sufficiently far from a condition that would make the material unsafe. How can we check the permissibility of a given stress? Well, if the stress sigma is uniaxial, we will simply check that sigma satisfies the inequality minus sigma c less than or equal to sigma less than or equal to sigma t, where sigma c is the allowable compressive stress and sigma t is the allowable tensile stress. The way to calculate the allowable stresses for a given material is described by the national or international building regulations, such as the Euro codes. These values are usually obtained by dividing the yield stress or the elasticity limits of the material by a safety factor greater than 1. The safety factor is aimed to allow for the uncertainties related to the material strength. For compressed bars, sigma c can be significantly lower than the elasticity limit in compression to avoid the possibility of buckling of the bar. In this case, the allowable compressive stress depends on the slenderness of the bar, and is as smaller as greater the slenderness is. If the material behaves symmetrically in tension and compression, as in the case of steel, the permissibility check is even simpler and consists in checking that the modulus of sigma is less than or equal to sigma 0, where sigma 0 is the uniaxial allowable stress. But in general, a body is subjected to three-dimensional stresses. How can we check the permissibility of a 3D stress? What we need is a domain of the allowable stresses in the space of the stress components, which encompasses all the points corresponding to stresses that the material can bear. Sometimes the allowable stress domain is called strength domain, but this term can be ambiguous. If the domain was obtained, for example, from yield tests on steel, a stress point outside the domain will not necessarily correspond to failure of the material, because the failure stress is higher than the yield stress. So just for the sake of brevity, we will use the two terms allowable stress domain and strength domain interchangeably. The allowable stress domain is defined by a function depending on all the stress components, which detects when a certain critical index is allowable or not. The choice of the critical index depends on the material. Each critical index corresponds to an allowable stress criterion, which is also improperly called strength criterion or failure criterion. We will now analyze some of the most common strength criteria, both for brittle materials and for ductile materials. Brittle materials such as concrete, mortar, brick behave differently in tension and compression. Conversely, most ductile materials such as steel and other metallic materials have the same strength in tension and compression. We will only deal with isotropic materials, that is, materials that exhibit the same mechanical properties in any direction. For these materials, any strength criterion can be expressed only in terms of principal stresses. We will not consider anisotropic materials like wood, fiber-reinforced materials, layered rock, and so on, which have different properties in different directions. For these materials, a strength criterion would also embed the orientation of the principal stresses with respect to the fibers or the layers, but we are not going to deal with these materials.